Hey guys, this video is a continuation and sort of recap of what we've been talking about in class right now, which is heat transfer. So, just to kind of give us some perspective here, we have our first law of thermodynamics, which we've kind of set out as probably the most important thing, almost like one of Newton's laws of motion, to help describe many things about thermodynamics. Remember, the word thermodynamics means, let me write this out here. The word thermodynamics means the movement of heat. Movement or heat movement. Now, something you really need to remember is that heat is energy. It's not hotness or coldness. That is our perception of temperature. Okay, so be really careful about this as we talk about energy. Thermodynamics and heat transfer is extremely important because it's the birth, really, if you truly look at it, of the glimpse into the quantum world. Think about a coil on a stove. When you first turn on the stove and you put your hand near it, you can feel the heat, but you can't see it, right? So you can feel this energy that is transferring somehow to your hand. But when the temperature increases, right, which is a result of sort of this electrical energy moving into this coil, what ends up happening is you start to be able to see the heat, right? And so the energy, the waves of energy that are being released from the coil have moved in on the spectrum, the electromagnetic spectrum. And at some point, we get movement up from the red hot zone up into the purple blue hot zone and then into the white hot zone. And all of a sudden, we are releasing ultraviolet sort of radiation. And that is where sort of the knock on the door to quantum mechanics came at the UV catastrophe, as it's known. So at this point, I just wanted to lay that out there so you can get an idea of, we're talking about the movement of energy. And here specifically looking at the random movement of energy. Because if you remember, for thermodynamics, work is orderly, right? It's ordered, and Q, or heat, is random. But both of those forms of energy, both an ordered transfer of energy and a random transfer of energy, result in the change of the internal energy or state of a system. So let's look at our three different methods of heat transfer. We'll start with our first one, which is heat conduction. Let's go to a new slide. Alright guys, so this first method of heat transfer is heat conduction. And this is an important one for solids. So this is the heat transfer for solid material. And the solids have to be in direct contact for this to occur. Otherwise, it's a different form of energy transfer. And what's important about heat conduction is that it's really heat transfer, so random energy transfer, by means of sort of a molecular storm, if you will, agitation from one material to another. So we have what we would consider our hot material, and I say hot with quotations because it's hot only because we perceive a higher temperature because the average kinetic energy of the particles is high. So I'm going to call it H for hot, and let's say I put it in contact with this blue box, which we will call cold or have lower kinetic energy. So let's write this as the kinetic energy of these particles is a little higher, the kinetic energy of these particles is a little lower, and hence we see a greater temperature here than we do over here. And this conduction is the physical sort of bumping into of the hot molecules, which are moving really fast over here, into the not so fast moving blue molecules over here. And when that collision occurs, obviously we have transferred some momentum. The momentum of the entire system will be conserved, but the momentum of the particles colliding will start to make the blue particles move a little bit faster. and they'll subsequently bump into different regions. And eventually what would happen after some time is we're going to see that the flow of heat from one object to the other is evened out. And when that happens, we would then describe, so in this dark blue color, that the temperature of both have become equal. And we would call this thermal equilibrium. Thermal equilibrium. So basically, how do you know you've reached thermal equilibrium? The temperature measured for both objects is equal. So that's, the basics of heat conduction. Now, excuse me, let's think about the rate of heat conduction. So the rate of heat conduction, if we want to write this sort of as a rate, let's move this up here. Let's think about what that's going to look like. Okay, so heat is Q, and anything that's a rate is going to be over some value for time. It's the change in heat, or the movement of heat over intervals of time, Q divided by T. And let's think of the different things that could affect that. Okay, what different things could affect the rate of heat transfer? Now, if we think about those two blocks that we had before, and I'm just going to make two random blocks, A and B. And we say that if the temperature of A is greater than the temperature of B, there will be a spontaneous heat transfer to block B. If the temperatures are equal, like we just saw in the previous section, then there will be no change in heat, or it will be even between. Now you have to be careful. It's not saying that there's zero heat, there's just zero transfer of heat, because the net amount of heat leaving A or leaving B is the same amount being gained by A or B. So we have a change in heat that is consistent. Heat will not spontaneously flow from the lower temperature to the higher temperature. The pink arrow won't happen spontaneously. And in class coming up soon, we're going to discuss that in more detail, the second law of thermodynamics and entropy. So what do you think affects the rate of heat transfer? Could it be possibly, so let's call the rate of heat transfer H for now, okay, just so we can get rid of some variables. Would you say that H is proportional to the difference in temperatures, delta T, from the one region, from the hot region to the cold region? Most likely, yeah, because if you had a greater temperature difference, you would have a greater rate of heat flow, which kind of makes sense. If you think of having a slide that has a high gradient versus a not so high gradient, you can think of a kind of how a ball would be rolling down that gradient. That's kind of how I think of it sometimes. If there's a greater difference between the top and the bottom, you're going to have a much greater rate of heat transfer. Okay, let's think about what else could matter. Now I purposely drew the block B smaller than block A. Would it make a difference if block B was this big and they were touching all along the edge of block A, instead of, I'm going to do this in white here, instead of just this little region over here? Think about that. Would more heat, random energy, be able to transfer from A to B if B was the green block versus the white block? You can pause the video, think about that for a sec. I would say yes. I would say that the rate of heat transfer is proportional to the area of the surfaces that are in contact with each other, or you could say the surface of the insulation. Because if you think about it, the more molecules that can collide would be found in a greater area, less molecules in a smaller area. So that makes sense. Let's consider some other things too, right? Say we had a barrier between these two blocks. Let's make block A a little barrier now, and block B. We're not going to make it super insulated, but there's some there is some space or something between them. Now if TA is greater than TB, we know we're going to have net flow from A to B, but will it depend on the thickness of this barrier? You guessed right, it would depend on the thickness. If it was much thicker, you'd have less heat transfer, or less rate of heat transfer. If it was much thinner, you'd have more rate of heat transfer. So we're going to say that heat is inversely proportional to the thickness. Let's call the thickness D. Alright, so let me move some stuff around here. Let's try to get this over this way. So we have so far these three proportions that we can reason quite well what that would sort of imply. So if we make a compound proportion, we have that the rate of heat transfer, which is H, so let me go ahead and write that out again, is proportional to A times delta T, T hot minus T cold, divided by D. Now if you collected data for a variety of different materials, what you would find is that if you graphed, rate of heat transfer, which would obviously be our dependent variable because we would be trying to see how that is affected, and on your independent axis, which is known as your x-axis, you could pick any one of these variables over here. But if we graphed all of those by collecting sort of regions or sets of data, what we would find is that the slope of the line that we get would be different for different materials, which is kind of interesting. Now the colors don't correspond to anything except that they differentiate each other from each other. So this line down here would imply that at a certain amount of area times difference in temperature divided by thickness of the barrier, you don't get as much heat transfer as you do for something like this really dark blue arrow up here. Okay, so the slope of that line is what we're actually going to call the thermal conductivity. And if you think about what we've talked about of other things before in physics, Physics 1 and in Physics 2, in Physics 1 in our sort of mechanics, you think about coefficient of friction, right? It describes the interaction between the surfaces. Now, it's material dependent or surface dependent. Now, this term, thermal conductivity, is not exactly the same thing as your mu, coefficient of friction, because this does have units, right? It's not just a ratio. It's a proportionality constant that describes the molecular heat transferable properties of different metals. Okay, so let's move to a new slide so we can just summarize quickly what we have. Okay, so really fast, we have rate of heat transfer, which is known as Q over time, change in heat over time, and we found that it's proportional to A delta T, area times change in temperature divided by thickness, and we just found that if you graph H versus A delta T over D, you get consistent slopes, linear lines for particular materials, and what that slope is on that graph is actually thermal conductivity. We use this kappa to represent that. So right now we would have a function H is equal to Q over T, which is also equal to kappa A delta T over D. Something with a high thermal conductivity, so a great constant, is going to obviously allow much more heat transfer per change in all those other variables. So this is a useful function that you can use to describe conduction through barriers, right? So let's think of just quickly some different thermal conductivities. Something like silver, copper, or gold, things that have very good electrical conductivity, okay? Those things, they have conductivities around. Silver is about 406, copper is maybe in the 380s somewhere, gold, lower 300s, brass, 100 and something, low 100s. Then we start dropping steel and iron, lead, mercury, and we finally start getting down to things like asbestos. Think about what asbestos was used for. Luckily, it's not really used anymore because of its carcinogenic properties. But it was used to insulate, right? It was almost like fireproof, if you would. It has a thermal conductivity of 0.08. So that means whatever amount of heat transfer you get in terms of area, difference in temperature, and the thickness of the material of the asbestos, you multiply all of that by 0.08, so it shrinks the amount of heat transfer by a lot, meaning it's a good insulator. Fiberglass is pretty good, 0.04, and then you get, many other things. Wood tends to be a very good insulator, usually depending on the kind of wood, 0.12 to 0.04. And then you get things like oxygen, nitrogen, gases, right? Air actually serves as a very good insulator. So oftentimes when you have a thermos, there's that gap layer in between the inner and outer layer, and that air is actually helping insulate. As you know, styrofoam cups, you don't have to put a sleeve on those like you do with cardboard cups. Now, polystyrene or styrofoam is very bad for the environment, but it has a thermal conductivity of 0.02. The units of the thermal conductivity are the watt per meter Kelvin. So you can kind of see how that would factor into the equation, into the function. Think about watts as being the rate of energy transfer. So heat transfer, Q over T, is really a measure of power in a sense, which is interesting, but it gets its own term because it is very specific to random energy transfer. Remember, you can also get work divided by time, which gives you the same sort of idea, except it's organized, an orderly transfer. Okay, so that's all the stuff about conductivity, thermal conductivity, and conduction, right? Now, we are not going to talk very much about radiation in this unit. In this course, we are going to spend a lot of time discussing radiation, more so when we get to the ends of electromagnetism, physical optics, and when we sort of break into the quantum and nuclear physics area. So we will come back and discuss that later. So we have just maybe about 6 or 7 minutes. I'll try to keep myself to that on convection. Okay, convection. Now convection, so we've got conduction as one method, we've got convection, and then we also have radiation. I like to remember those as one of my favorite bands, CCR, Creedence Clearwater Revival, so CCR. So convection is heat transfer by sort of the mass motion of fluids. You can think of fluids as like air or water or any variety of different fluids that we've talked about. And basically what happens is when heat is provided from some sort of energy source, so from burning gas or from an electrical stove, when the water, let's use water for example, we have a big pot of water on the stove. The water that's closest to the heat source receives heat through some sort of conduction to those water molecules, and as they start to get more and more excited, obviously you can imagine that water is going to start to expand. And according to our ideal gas law, PV equals nRT, as heat is added, we know the velocity of the molecules is going to increase. Therefore, the kinetic energy of the molecules will increase. Therefore, the temperature will increase, which is going to cause the volume to expand. And as those particles expand, going back to some density here, as the gas or the liquid expands, the density drops. And as we know from Archimedes' principle, less dense things are going to float. And so we're going to have these heated up molecules down here. And what we mean by heated up molecules is that they have more moving energy. They're going to start to expand, and so they're going to rise in the system. Now, as they move throughout the rest of the system, they're transferring energy microscopically to what we would consider the colder molecules or the less fast-moving molecules. When they get to the top, because they bounce into these cold molecules, if you will, the ones that aren't moving so fast, they transfer momentum. When that happens, then they lose some of their energy. Let me get a different color here. And the volume starts to drop. So we have rho equals m over volume. The volume now starts to drop, so the density increases, and those molecules start to fall back down again to near the heat source, which is over here. And when that happens, you can imagine the cycle continues. Again, these get really excited, the volume increases, the density drops, and they float. When they get up here, they transfer their energy to the things that aren't close to the heat, so not moving so fast, and then their volume decreases, density increases, and they sink, and the process continues over and over again. And that's why hot air rises and cooler air drops or falls. And this is a convection current. Convection currents are found in so many different areas, in the body, in storms, in convection ovens, for example. They have a fan that helps speed this process up, and so it can cook the food quickly, and a lot of people would say sort of more evenly as well. So that's basically heat transfer by convection. So it's happening primarily in a fluid or a gas, a liquid or a gas, so a fluid, because you have to have particles that can move and experience the ideal gas law proportion, if you will. A solid's not really going to do this unless it changes phase. Okay, so let's go on to our very last slide now. So we've got a few minutes. What I want to look at here is a quantity of heat. So how would you say, how much heat do I need to change the temperature of something? So let's start with just proportionality. If you have a lot of mass, so if you're trying to heat a big pot of water versus a small pot of water, you're going to need more heat for more mass. So those are directly proportional. If you're making a greater temperature change, you're going to need more heat, which makes sense to our experience, I would say. And then the property of the molecular sort of property of the material also relates, and we're going to call this C being specific heat. And specific heat is a term, a specific amount of heat, okay, to a certain molecule or to a certain kind of compound or a certain element or chemical makeup of that specific substance. So something like water has a large specific heat, 4,183 joules per kilogram Kelvin. So that means it takes 4,183 joules to raise 1 kilogram of water up 1 Kelvin. Not 1 degree Kelvin, just 1 Kelvin. You could also say up 1 degree Celsius, so this delta T can work both ways. As long as both T final and T initial are both degrees Celsius or both Kelvin, the delta T would be the same, because a 1-to-1 ratio. So this equation, very fast here, is going to be this. Now, I'm kind of rushing through this because I don't want to belabor it. We have a lot to get through, but this is a useful equation to many pre-med kids. This holds special meaning because it predicts their future. The MCAT, you can see, is in there, Medical College Admission Test. So that is describing how much heat, Q, is needed to change the temperature, delta T, of X amount of material, M, of a specific molecular structure, C. And so water is used often as a very sort of strong, or requires a lot of heat to make it increase in temperature. So it's often used to cool things. If you run water through even nuclear power plants, that's usually why they're built near water, is to help keep it cool. Because if you can keep water running through, if the water takes a lot of heat, a lot of energy to increase its temperature, it will always be, hopefully, less temperature than the machinery around it, and the heat will always flow, like we said with conduction, always from the hot, or the thing with the higher temperature, to the area with the lower temperature, which will hopefully always be the water, because it requires so much energy to even increase it 1 Kelvin. So that's what this function is used for. And what you can do with it that's kind of cool is that, say you have a beaker full of water and it's at room temperature, and you dip a copper rod that's really, really, really warm in the water. Now we know that the heat is going to flow randomly from the copper into the water, and the water is going to get warmer, right? It's going to receive more energy, and the temperature will increase, and eventually at some point they will be at thermal equilibrium. But what we can say is that the Q from the copper, so let's do Q subscript Cu, is equal to the loss of that heat is equal to the gain of that heat by the H2O. So you can set mc delta T of the copper, or negative mc delta T of the copper, equal to mc delta T of the water. And knowing various pieces of information, you can solve for anything really you need. The final temperature of both will be the same. So when you expand the delta T, you're going to get T final minus T initial, and on both sides of the mega sort of symmetry equation, the negative Q equals Q, TF will be the same on both sides when they finally reach thermal equilibrium. So I'm not going to summarize the video, it's long enough, but we basically got 3 types of heat transfer: conduction, convection, radiation. So go back and look through things again. Make sure you're familiar with that stuff. There are a few little important equations in here. Not all of them are always provided on exam sheets, so you do kind of have to know. But I think they make pretty good logical sense. All right, enjoy, good luck. See you in class.